welcome, Elena. Thank you very much for presenting here your work in our lecture course. And yeah, Elena de Momi is instrumental in the development of robotic systems, especially in the medical field, in the operating theater, I would say. So the way I see it is you have been working quite a bit in bringing these robotic devices to the operating theater, kind of integrating them into the workflow there. And I see you are also looking at the interaction between these robotic devices and the human, I suppose mainly the surgeon, but hopefully also the patient. And yeah, so I look forward to your presentation. The floor is yours.
Thanks for the introduction, and thanks to the attendees for attending this lecture. I decided to focus the talk on some of our research, which is particularly interested in developing autonomy for surgery. In order to do that, we have to transfer the knowledge from the human experts, so from the surgeon, to the robotic assistant, so that the robotic assistant can play the role of an effective assistance of the surgical operation. So I'm just would like to have some introduction on our lab activities. So we are two faculty people and a lot of PhD students and postdoc. Some of them are here in the picture, which we took last year. There will be another updated picture in the end. And these are the main research lines of the lab. So we do human-robot interaction. We deal with soft robotics and with decision support system in order to help the medical doctor to take decisions on the proper treatment for the patients. Everything is embedded with augmented reality and with artificial intelligence, and I will explain you how. So this is a snapshot of the settings of the lab. We are part of Leonardo Robotics Laboratory with other colleagues of the department dealing with the human-robot interaction, with the robotics in industry, and in our section we do medical robotics. So robotics for surgery, for assistance, and with another colleague of mine, she deals with the rehabilitation. And so this is some pictures taken in the lab where we have basically these two main setups. One is the Da Vinci system. We have also a serial manipulator that you can see here in the picture. So let's start the talk with a brief introduction on what is the surgical data science, and which brings us to explain the evolution of surgery. So in the past, there was the surgeon was alone with the patient using some let's say some instruments which were not connected and were not so the signal were not automatically acquired. In the future surgical room, all the instruments that are used by the surgeons will be connected with each other. Most importantly, the video stream, which is up to now digital, which we will entail a lot of information which can be automatically processed and offered to the robotic assistant, for example, to increase the safety of the surgical operation. So this concept has been studied and presented by a consortium in Europe, which is dealing with this problem of surgical data science. There is this interesting website in which you can find a lot of information about it. The importance of using the video stream for safety can be explained by this video. So listen to the beep, which is taking place here, so well before the accident happens. So I've been recently encountering this video, which I find extremely interesting, because it shows that the automatic processes of videos, which can be faster with respect to the human situation awareness, can increase the safety. So if we can translate this concept of situation awareness done by the computer to the surgical theater, we can develop systems which are safer than the surgeon itself in performing the surgical intervention. To do so, We need not only to process the images, but to embed this processing with knowledge. So knowledge is not just information. Knowledge is the ability to apply the information which is embedded in the signal. And the knowledge transfer is the process through which we can transfer the knowledge from the human expert to the autonomous system, so to the computer, to the robot. In general, artificial intelligence entering the surgical field has been, let's say, done through these two paradigms, machine learning and reasoning. So machine learning is a bottom-up process through which we start from data and we derive information from the processing of data. So, for example, from clustering of information, or through the detection of regions, or through the detection of particular kind of information from the images, for example. So images are just an example of data that we can use in the surgical theater. We have all the clinical parameters, for example, of the patient, which embed a lot of information. The other approach is a top-down approach, in which we know the rules of the game, and then we translate this human knowledge, so the expert knowledge, into rules so that we can pass to the robotic assistant. The loop is closed by result interpretation, because in the bottom-up approach, we need to have an explanation of the results. The results explanation can be derived through the top-down approach, because in the top-down, we know already what are the rules underneath the process that we are trying to process. And so this result interpretation is being called like explainable artificial intelligence. So let's go back to the concept of autonomous driving and the possibilities that autonomous driving is offering with respect to standard driving. So as I said before, automatic processing can increase the safety. And in the automotive industry, this concept of automation to increase safety has been classified with different level of assistance, from the level 1, in which we have, for example, lateral control, whether if the car is, for example, overcrossing the lines, or we have some autonomous braking system if, for example, we are too close to the car which is in front of us. But between these simple assistance and the fully autonomous car, there are other different levels in which the driver can, for example, be distracted. For example, can also have the eyes off or the hands off. These 3 and 4 levels are the most dangerous one, because it's difficult to maintain a balance between what is left to the human and what is left to the autonomous car, to the autonomous control. In the same way, you have seen also in the presentation of Professor Fiorini, the same translation of a different level of automation has been translated in the robotic surgery domain, and this classification with the 6th level of autonomy has been recently put in a nice paper by DuPont in 2022, in which you can see that you have the same level of autonomy, so from no autonomy to the first level to fully automation, the current let's say, scenario and the future scenario in different surgical specialties, in different clinical domains. And as you can see in this picture, the number of possibilities offered by the artificial intelligence to get to an autonomous system is increasing in time, and in the future will entail more and more operations. What is the situation for the medical, so to the regulatory aspect? So can this autonomous system be approved by the regulatory aspect, so as FDA, for example, and CE mark? Of course, because if we prove, so if this system, autonomous systems, undergo the same certification process as standard medical devices, these systems will be approved, and it has already been happening with some of the systems for example, diagnosis which have been cleared from the FDA because they proved to be robust enough also to detect, for example, some lesions in particular images. So the process is undergoing, and for sure there will be, let's say, a happy ending, at least for some of the applications in which the safety and the, let's say, decrease in the possible medical error will be proved. What is the situation in Europe? In Europe, the European Commission and also the scientists in Europe have been debating about the reliability of artificial intelligence, and the document that was released some years ago speaks about some ethic guidelines for trustworthy artificial intelligence. So this is a keyword that it's really, really important. The robustness, reliability has to be proven. And there is also this aspect of the human oversight. So there should always be the human, let's say, monitoring that the system is fair and properly working. So let's go now into the research topic about my talk, and I will explain you some of the use cases that we have been approaching, in which we are trying to transfer the knowledge from the expert to the robot in order to get an autonomous robot. I will explain you with 4 examples. The first one is the endoscopic camera motion. So I think that in the previous talks, you've been already introduced with the concept of the operation of endoscopic monitoring of the operation in minimally invasive surgery. So usually the endoscope can be, in standard surgery, is held by a passive holder, or there is the presence, for example, of a human assistant to move the camera of the endoscope while the surgeon is performing the intervention, moving with his 2 hands or her 2 hands the surgical instruments. In robotic surgery, the endoscope can be held by a robotic holder, which is commanded by, for example, by foot pedals, voice control, gaze control, and head movements. In particular, the Da Vinci system has foot pedal control, which allows the switch between the control of the instruments and the control of the holder. While, for example, other systems like the Senance from Transenterics, they have gaze controlled and head movements which control the motion of the endoscope. So all these, in this scenario, one of the research lines that is being followed in the recent years is to provide an autonomous control of the endoscope, which should be, let's say, smooth, and shouldn't disturb the action. Actually, it should improve the performance of the task, and proper benchmark measures, performance measures has to be designed in order to understand whether this autonomous control is effective or not in the task execution. So the first setup that we tried was automatic control of the endoscopic camera. So the control was just, so the autonomous control was very simple, was positioning the center of the image of the endoscopic camera at the center point between the 2 surgical instruments. So in order to prove whether this automatic control was effective or not in the completion of the surgical task, my students designed this complex scenario in which we used ex vivo material, and the surgeons were asked to come to our lab to perform standard surgical operations on this ex vivo material. And you can see here some videos of the surgeries which were performed. So the procedures which were mimicked were this retrovesical anastomosis, and the tissue that was used was a chicken esophagus and the chicken stomach. And you can see in the two images the different control of the camera. So the standard control with the foot pedal activation and the autonomous camera motion, which was adjusting the camera position at the center of the 2 surgical instruments. So the second procedure was the orthotopic no bladder reconstruction, mimicked using the pig bowel structure. And this was the surgical task. What were the results which we collected? So we had 10 users, so 10 urologists coming to the lab, the 10 urologists with different surgical experience. What we proved was that there was, of course, the motion of the camera was more control, so was less with respect to the manual control. And the time out of the field of view was less in autonomous mode with respect to the standard operation, so the standard foot pedal control. But what we also measured was that there was not an improvement in the completion time. And also when interviewed, the surgeon reported some, let's say, dizziness and confusion using the system because of the continuous motion of the camera, which they were not used to. So another student, Nicola, who just came back from Johns Hopkins University, was advanced in the study and proposed a tailored control on the camera motion with respect to the gesture that was performed by the surgeon. So the task, which was a simple suturing task, was decomposed in 4 different phases, and the motion of the camera was tailored according to the phase of the surgical task. As I said, it's also important to understand the right performance metrics to measure whether we had an advancement, an improvement or not with this autonomous control, and some objective metrics were defined, as well as the subjective metrics, again measured using these NASA TLX indexes. So with respect to the previous system, which was the scan methodologies in which the camera was following the middle point between the 2 instruments, we can see here that we have an improvement in the completion time of the task. Of course, as we were commenting just a few minutes ago, in this case, the surgical task was limited with respect to the surgical action that was performed on ex vivo tissue in the previous slide, so in the previous experiment. So further tests are needed in order to understand whether this tailored control of the camera is really providing an effective improvement with respect to the continuous camera motion or to the traditional one with the foot pedal. Another just a bit of information about controlling the camera, the endoscopic camera, can be also translated in neurosurgery, where surgeons are performing operation directly looking at the inside the microscope, but not using robots, but using their hands. So it's a manual operation done through the microscope. In this case, again, the microscope is mounted on an arm, on a passive active arm, which is moved using a foot pedal tray. In this case, we wanted to perform manual operation, autonomously controlling the microscope. So this is the setup that you are seeing here. We mounted a camera, a 3D camera on top of a KUKA arm, and we are automatically recognizing the position of the instrument using some computer vision tools, because we need fast recognition of the position of the system, and we need a fast control loop which adjusts the position of the endoscope without perturbing the action. So we have to pay attention when changing the orientation, especially the orientation of the camera, so that the surgeon is not distracted and is not increasing the cognitive load of the task execution. So preliminary experiments done on this mimicked task. So you can see here we have this ring which needs to pass from a starting point to an end point, adjusting the camera view according to the position of the instrument. And with respect to the standard control of the camera position through the foot pedal, we are getting better results. So another, let's say, another scenario in which we need to translate the knowledge from the expert to the robot, in order always, our aim is to find solutions in which autonomy can increase safety, is to try to perform this transfer of knowledge, teaching the robot, for example, to design some simple trajectory. And the idea of my PhD student, Junlin Fu, was to improve the teaching, let's say, to offer a teaching instrument to the user using augmented reality. So the user is teaching to the robot to design a simple trajectory in space, respecting the RCM constraints, so the remote center of motion. The surgical tool has to pass through this remote center of motion and has not to perform any, let's say, contact between the instrument and the hole and the trocar port. So the task that has to be learned is path planning together with some constraints in motion of the surgical tip. And the teaching from the user is improved because the user is also seeing the hologram of the robot while teaching the trajectories through through an instrument which was optically localized. So apart from the complex registration procedure between all the localization systems, the hologram, the HoloLens, and the surgical robot, this is what we get. So we compared the standard kinesthetic teaching, which the user is maneuvering the robot with the hands, performing the desired trajectory, compared with the augmented reality, the augmented teaching, in which, as I said, the user is seeing either the trajectory to be learned and the hologram of the robot, respecting the RCM constraint. In these preliminary results, we demonstrated that we get, let's say, an easier transfer of knowledge between the user and the robot and better trajectories performed by the robot in terms of desired length or desired path with respect to the ideal trajectory that the robot has to design. And this is a video in which the robot and the user are cooperating to perform this simple task, respecting the RCM that you can see here. So now let's switch to the last part of the talk, in which we are introducing another concept of learning, of transferring this knowledge, which is done through inverse reinforcement learning. So what is, and we are applying this concept of, let's say, transfer of knowledge to soft robotics. Soft robotics, which are curvilinear steerable catheters, which can be inserted through soft tissue or through lumen and perform operations in a minimally invasive way. So the concept here in neurosurgery is that, for example, we need to reach a target which is set depth inside the brain through a catheter, which can be, in this case, was a rigid probe, but in our project, it was a steerable catheter. Steerable catheter, with respect to a standard rigid probe, offer the possibilities of numerous trajectories with respect to the single trajectory, starting from, for example, from the single entry point. The catheter that we used was a steerable catheter, able to perform, as I said, curvilinear trajectory inside the brain, and the aim is to get to the target, avoiding all the obstacles around, which are represented by the vessel tree. In general, in our setup, what are the inputs? So the input are the preoperative images through which we can set the target and the obstacles, which are the regions that we need to avoid. The path that we have to undertake has some constraint, which are represented by the obstacle and the kinematic possibilities of our catheter. In our case, we had a minimum radius of curvature that we had to respect because of the kinematic constraint of the catheter. And the objective is to compute the shortest and safest path, so the path which guarantees the maximum distance with respect to the obstacle. So it's a clear path planning problem, which we solved through a learning approach. So in general, in reinforcement learning, you have an agent, so an actor, which is represented by, in this case, in our case, the agent state. So the agent state was represented by the current pose of the tip of the robot. You have an environment. In our case, the environment was represented by the 3D volume of the brain. The agent can perform actions in the environment, changing its state at each iteration. So the state is always changing while the agent is proceeding from the entry point to the target point. And the agent behavior, so the agent actions, are controlled by some reward. So the agent gets a reward if the path is far away from the obstacle and is getting closer to the target. So this is in general the standard reinforcement learning approach, which you can see also implemented here in this popular game. The approach that we are embedding in our research is the inverse reinforcement learning, in which, apart from the standard schema of rewards, environment, and behavior, so behavior is dictating the actions of the system, we are inserting an expert. So the expert is actually the person who is designing the best behavior for the agent. So the expert, for example, in our case, was designing the optimal trajectories, so the optimal path for the agent to be undertaken in order to get to the target. So let's see the same concepts translated in our setup. We have, so the clinical problem which we were facing was convection-enhanced drug delivery. Means that we need our carrier, so our steerable robot, to get to the tumor with a particular pose, so that the carrier, which was also carrying the drugs, so the pharmaceutical agent, which would deliver the pharmaceutical agent to the tumor with the right entry point, let's say, and 3 directions, so that the drug could be easily distributed in the tumor. We were using a steering catheter, which was developed by Imperial College. And then so the tumor is the target. We had to respect the catheter constraint in terms of curvature possibilities and to avoid the vessel which would encounter along the path toward the target. So this is how we model the situation. So this is the 4-segment catheter, which you can also see in this video, entering some soft tissue mimicking material like gelatin. So the catheter was modeled with the 4 segments, and according to the segment which was advancing most, you can design different paths inside this soft tissue, because you have that the resistance of the soft tissue is actually allowing the catheter to design curves. So the actions of the catheter are represented by the pose of the reference system, so the pose of and at the end effector, so the distal part of the catheter. We had constraints in the maximum curvature and constraints on the dimension of the catheter, which should be respected in the path planning. And the expert was teaching desired trajectory through an interface. So the expert was commanding this joystick in a simulated environment to teach the best trajectory that the system should mimic and learn. Of course, the system should be able to generalize to, let's say, starting point or to situations not seen before. So the system is not just mimicking, replicating exactly what the expert was teaching, but has to be able to generalize to unseen situation. Another, let's say, feature that we added, but I'm not, let's say, going into details about this, was that we also included in our best path computation some rules which came directly from the expert to the system, so that some trajectories were discarded in the end because they did not satisfy some of the rules which were not embedded in the automatic computation. So this is a video of what was achieved. So this is in general the integrated system in which the catheter was delivered to the entry point and then automatically reach the target. And this is the interface that the expert was using while teaching the best trajectory to the system. So the user was using, as I said, this joystick, was navigating virtually inside the brain, teaching the system what were the best trajectory to be learned. So this is the path that we try to teach to the system. These are the performance metrics in which we want to get to the target with a particular orientation of the catheter. And this is the video that we got when we put the system in gelatin in order to reach some targets which were designed, let's say, in this simulated environment. What I'm trying to say here is that we were learning in a simulated environment, and then we are transferring what we were learning in simulation to the real case. And so this is the transfer learning between let's say, digital model of the brain to the real case, which in this case was just some soft tissue mimicking brain material. The digital model of the brain was then was complicated a bit further, including this simulation environment, which is embedded in Unity. It's acceleration engine, which is called NVIDIA Flex, and the brain structures was modeled as a soft material in order to understand how brain deformation might affect the path while the catheter was inserted in the brain. So this study was interesting because we performed this comparison between the simulation performed on brain tissue, but also on the animal that we actually use in the experiment, which were sheep. And we compared the simulated results with respect to the situation that we got after the insertion of the catheter on 5 sheep. And the displacement of the brain tissue was measured via post-operative magnetic resonance. And from the images, we got this real deformation field together with the University of Munich. And we compared the actual displacement as we compared with the planned displacement of the brain tissue while the catheter was inserted. And these are the sampling points which we use to compute the displacement. And the result we achieved demonstrated that our model, our digital copy of the brain, was quite similar in behavior with respect to the real brain behavior. So this is the final video that we have of the entire system. So it was a very long project in which we were, as I said, responsible for the path planning and control, partly of the control of the catheter in movement inside the brain. And the project had, so the other partners were, the coordinator was Imperial College, we had the TU Munich, was University of Groningen, and medical partners here in Milano was the vet surgeons and the University of Milano with the neurosurgeons. So this is the catheter model advancing and avoiding the vessel to be inserted and controlled, so to reach the target, having so to respect safety boundaries. And so this is in the final part of the video. You can see that the system was actually put in place. So these are the actuators of the catheter. So the actuators are the metallic part, while the catheter was the last part. You can see these colored wires here compose the catheter. So the 4 segments of the catheter, which was inserted in the sheath. So, and here the operations which were performed on in vivo animals, which were so completed at the end of the project. So the last piece of information regards the translation of this reinforcement learning approach to cardiovascular domain. In this case, we are exploiting also augmented reality to safely perform endovascular operations in order to have structural intervention to the heart. So the project here is another European project we are coordinating as Politecnico di Milano. So the problem here is, so we are not advancing in soft tissue, we are advancing in vessel, and we need to replace the mitral valve. In order to get to the valve, we are crossing the septum, landing on the mitral valve, and with the catheter, and placing the valve so that it can substitute completely the let's say the damaged valve. The current approach uses this system, which is called the MitraClip. It's a tendon-driven catheter, which is manually operated by the cardiologist through some handles which maneuver the system. So the system is really complex to be operated. So the idea here was to robotize the actuation so that the system becomes completely autonomous and follows the safest path through the vessel and to the heart in order to perform the operation in a safer way. So we have been working since 1 year, and these are some of the preliminary videos of the system with the actuation system. So the handles were substituted with the actuation stages. This is so the catheter has been embedded with sensors, either electromagnetic sensor and FPG sensor, so optical fibers inside the catheter to detect the curvature of the catheter. And this is the visualization system. So the idea is to try to get rid of the fluoroscopic images which are undertaken during the operation in order to decrease the invasiveness of the procedure. And the surgeon is wearing the HoloLens devices, so an augmented reality interface, which is showing the structure of the vessel, because you have to think that the patient is lying and covered on the operating table, and the surgeon is able to overlap the vessel models and the catheter models on top of the patient through this augmented reality visualization. The path planning, either in the vasculature phase and in the heart phase, is done via inverse reinforcement learning. So again, the expert is translating desired trajectories to the system. The system is able to learn and to generalize its behavior. And these are, again, preliminary results in terms of the last phase of the path planning. So when the catheter has crossed the septum and has to land properly to the mitral valve plane, so that it's perpendicular to that plane and gets to the right pose in order to open then the replacement of the mitral valve. So I almost finished my talk, and I just wanted to give you some take-home messages in this concept about transferring the knowledge from the human expert to the robotic system in order to have autonomous system which can increase the safety of the surgical operation. So, of course, this process has some risk, because we might have some cognitive bias, because we are collecting the experience of some particular bunch of experts. So in this transfer of knowledge, we need to pay attention to generalize also the knowledge, for example, from different surgeons with different expertise, and so on. In order, there is a problem, as I said before, in certification, but this problem can be overcome providing proper validation of the system. So if the system undergoes the same validation procedure and the same robustness certification of standard medical devices, then certification can be guaranteed. But as I said, it's a problem of robustness. So the system has to be, let's say, to solve properly also situations which have not been met in the learning phase. The benefits of autonomous system or robotic system in surgery in general are related to the standardization of the process, because we are providing same level of, let's say, treatment across different domains, across different expertise. So expert and non-expert surgeon can provide the same level of treatment to patients. We can also exploit this concept in training. For example, in the augmented reality setup that I've just described, in which the surgeon is using, for example, the augmented reality to maneuver the complex mitral clip system. This system can be used for training. So the surgeon, instead of maneuvering just the system, has a feedback about how to maneuver the mitral clip, and also can be taught about the best trajectory to implement on the patient. As I said, the final goal of our application is to increase the safety of the interventions and to decrease possible surgical error. So is this human-centered approach the solution, and whether this human-centered approach should be shared or completely autonomous is still an open question. And I think that it should be balanced according to the different applications. So in some cases, completely autonomy is welcome. In some other cases, there should always be an oversight by the surgeon. So this, as I promised, there was an updated picture of the people working with me. So I have a lot of PhD students and master students who are developing amazing research in collaboration with our collaborators in Italy and around the world. So we have been blessed by a lot of interesting collaborations and projects in the past. And I'm just leaving you these two other bits of information. So this is what artificial intelligence is able to do, machine learning in general, computer vision in other surgical domains. So this is colonoscopy, and this is microscopy in neurosurgery. So in one case, we have the reconstruction of the colon surface thanks to the some SLAM techniques, and on the right-hand side we have the panoramic view of the brain, just moving the microscope around just teaching the images of what the microscope is seeing during the operations. So again, I thank you for your attention, and I welcome questions and curiosity.
Thank you very much, Elena. Fantastic presentation, and yeah, thanks again for presenting your work. I think very useful information for the students about your approaches, especially to path planning and how to incorporate the cognitive abilities of the surgeons, which is somehow available, but we need to extract it and make good use of it. So excellent. Thanks a lot for that. Yeah, I hope it's okay if we spend a few more minutes on questions and answers. So I open the floor to any questions that you might have. So those in the classroom, please raise your hand, and those online, you can also, put your hand up or open the microphone. I mean, I have many questions written down here, and maybe I can get started with those. I don't know whether we can get through all of them, but yeah. Yeah, so I would like to know So you spoke about certification, and that has been also a topic with other colleagues beforehand. And in the past, my feeling was that that was a big issue, because especially when we start using AI is like a black box. We have a neural network in there and we don't understand that. So you spoke about explainable AI, but how explainable is it? Can we make sure that this system will react appropriately also in situations that it hasn't seen beforehand?
Okay, the answer is no, we cannot make sure the system is able to, let's say, properly behave with some situation not seen before. But when you have to think about certification of a device, so also a device which is aimed for a purpose cannot behave properly when it's let's say, meeting something which is not expected. But the example I like to think about when thinking about certification issues for system embedded with artificial intelligence is, for example, the smart endoscope. So, for example, in colonoscopy, there is this product already on the market, which has also found some, let's say, let's say, positive comments from surgeons, is the smart endoscope for colonoscopy, which is a system now, so was designed and then was put on the market by Medtronic, so it's called the GI Genius. So that system was trained with numerous images of colon. It's not providing classification, just detection. So you are passing the system through the column and you just find a box when a polyp is detected. And this system is not taking any decision. It's just alerting the endoscope there is something that he should see well. So it's just an assistive device, because the endoscopist is looking at the images. But in case the endoscope is tired or distracted and so on, again, his attention is pointed to the polyp. This system got certification because its performances were compared with standard, let's say, procedure. So there was like the standard certification process in which you prove the safety and efficacy of your product with respect to the standard care, and so with a sufficient number of cases. So when you fulfill all the documentation, let's say the standard process of getting certification, it's like another medical device which is undergoing the same process.
Okay. Yeah,
So,
no. Sorry.
Yeah. So I think that the same will be done with all the others, let's say, features that you are getting to the system. So the same problem was, for example, when this Tesla car, which was detecting the accident well before it was happening. So the system is now embedded in the Tesla car, and also the automatic braking was implemented in the Tesla car. So I think that the trick is that so the autonomous actions should be always a conservative one, like, for example, braking or just alerting about the possible polyp and so on. So if it's just something that it's not, let's say, acting any possible damage, it's just a safety mechanism.
Okay, yeah, that makes sense. And I mean, in particular with detection and even classification, I would say we should more and more rely on these new technologies. But now when the system is asked to act, I mean, you made the example of the Tesla car, and that's useful, I agree. But what about now actively carrying out a procedure? Will that also come one day, that we rely on AI to do suturing or to do cutting, for example, of tissue?
So, for example, in the Tesla car, the system was just braking. So the system was stopping. So it's not performing any action. It's, let's say, avoiding an accident.
True, but there could be a car behind.
Yeah, sure. But in case you are, let's say, stopping, you have to stop, let's say, with some constraint, let's say, to not to sleep on the street and so on. In case of suturing, I would say that you would go for the automatic suturing when you demonstrate that automatic suturing is safer with respect to manual suturing. At that point, you will choose the other one.
Okay. Yeah. Okay. Yeah. Yeah. So I take your point. You know, we just need to provide the evidence that it's safer and more reliable than what a human can do, and then I suppose we are there. Yeah. I'm just looking around. No question at the moment, but then maybe I continue. Or is there a question? No. You spoke about. I'm coming back to the automatic control of cameras doing surgery, and that looks also very interesting. And you showed that it improves on quite a number of aspects. So it reduces the mental load or the mental demand, the stress is reduced, and the time to do a certain operation is also much shorter. So I'm wondering, and so that looks all very positive, but I'm wondering whether you're also speaking to surgeons and to see what their opinion is on that.
Yeah. So the first trial was performed by surgeons. So there were 10 surgeons. And as I said, so the comment was that it was a kind of disturbing because the camera was continuously moving while the instruments were moving. So that's why the second approach was try to find another control schema which would affect less the motion of the camera. So be closer to what the surgeons would do. So for example, in some cases, just moving the field of view, so the focus, just let's say playing on the zoom of the system is, let's say, something which could advance. So let's do less, but try to have an incremental approach in order to, let's say, to find effective criteria which measure the best completion of the task. Yeah, so something that it's not easy to be demonstrated because it depends a lot on the cognitive load. So for example, and also when you are designing a setup, let's say it's on one side, the setup should be easy because it's simple so that you can better understand what are the variables influencing the results. In the other case, surgeons are used to complex setup, for example, the one that we mimicked using ex vivo material. But in that case, maybe the variables are too much and it's not easy for us to understand whether, let's say, the problem was the movement of a camera in particular situations, or, for example, the cognitive load, you can measure the cognitive load, for example, measuring the reaction time to, let's say, unseen events or unpredicted events. And this is not easy to be, let's say, to design a setup in which we should interfere with the system to measure how much time the surgeon requires to face the unexpected situation.
Yeah. These are complex situations, obviously, and so it's not only the camera. I completely agree. Yeah.
Yeah.
Just wanted to maybe quickly go to your steerable catheters and that you move through the environment, and obviously you have them bendable so you can avoid damaging any healthy tissue on the way to your target. So you're using reinforcement learning and inverse reinforcement learning. So what are you training there? What is it that the system is learning? And added question: don't you need a very good model of the environment for this to work?
Yeah. So so what we are learning is that we have something that we are taking from experience and some, let's say, pre-coded rules. So something that we are taking from the experience is the examples from the surgeons. So the surgeons are maneuvering the some joysticks, for example, and teaching the system what are the desired path. But then we have also pre-coded information because the rule of being far away from obstacles or the rule to get to the target with some particular orientation and so on is something which comes from the, let's say, previous knowledge, so our rule-based system. And the second question was
the environment. It has
yeah, the environment. So yeah. So yes, you need the perfect modeling of the environment if you want to be robust. But in our case, we demonstrated that, for example, with soft tissue, we were able to mimic quite well the brain behavior, because either in case of deformations due to the crossing of the catheter, we made the experiments with the brain chip, and then it was well matched. I think that the robustness of the system can be, as you said, you need a lot of demonstrations, and demonstrations can be done if you have a perfect knowledge of the environment. You can also, let's say, insert your schema with, let's say, some traditional control loop in which you have the sensing on top. So in our cases, for the cardiovascular approach, we have ultrasound, we have the EM sensor, we have the FBG. So we know where the catheter is with respect to where the catheter should be. And also you can control, you can close the loop with some standard control schema. So I think that the solution is always to combine the approaches, the model-based and the model-free.
Yeah, good. Okay, then maybe just a quick question at the end. So you're using Unity, which is usually used by game developers, but you are using it with good results. So my question is, how realistic is it? I mean, is it providing a good engine there for modeling the brain?
Yeah, the realism is good. So we proved with experiments, even in the modeling of the vessel and the modeling of the brain. But realism does not come from biomechanical properties. So there is no way that you can translate for example, the elasticity in terms of expected behavior of the system, because you are playing just with the radius of the spheres, for example, and the distances between the center of the sphere. So it's something which is just for graphical, let's say, interactions and for games and so on. But you can tune those parameters, even if they don't have a biomechanical meaning, so that the final behavior resembles the one that you would expect, and it's fast. So the idea is that you don't need the FEM simulations with take ages or the mass springs, which still are not maybe real time. This system is real time.
And it's freely available, I think. Yeah.
It's available. It's open source.
Yeah, fantastic. Good. A quick look around, but there seems to be no other question. So thank you very much again, Elena. It was fantastic, and yeah, thanks for giving up your time to present to us.
You're welcome.
Fantastic. Thanks a lot.
Thank you so much.